um, we have been at this for the last 3 years, and I'll walk through our journey of how this came by and the transformation process, because we are not quite a startup. We are a 325-year-old bank, right? So trying to steer a ship as large as that is quite a challenge. And what we'll do is I'll walk you through our motivations and the core principles of doing this, and then our journey of how we did the transformation, and then finally we'll round it off with talking about a few gochas and things that tripped us up for sure, and we'll go from there, right? But a little bit about me, right? I've worked with a bunch of companies right now. I've worked for BarclayCard. I used to work for a consultancy called ThoughtWorks for a very long time, over a decade. And but my real claim to fame is that, if you're wondering why I have this picture of containers here, because I've been working with them since '97, right? Containers these days don't actually mean these physical containers. When I started, they actually were marine containers. So we used to work on a system where we would take containers, unberth them from ships, put them in the yard, plan where they need to be put in the yard, and then we had to ship them off somewhere inland or maybe on another ship and so on. So this is these are not the Linux containers. So it's true that I have been working with them since '97, right? Anyway, talking of ships and containers, right? Anybody know which ship this is? Sorry? Queen Elizabeth? No, not quite, right? How about this one? This is the RMS Titanic. You're right, right? So the thing about the Titanic is that it was when it was made, right, in the early 1900s, right, was made to be the biggest, best ship in the world at the time, comfortably, right? In fact, the manufacturers made 2 more ships like this. One was the Titanic, and the other was the one that you just saw in the previous picture. It's it was built in such a way that they felt that it was practically unsinkable, could not sink, right? In reality, it's impossible to even build that kind of a ship today, where you can claim it to be unsinkable. But at that time, they were so confident about it that they said it wouldn't sink at all, right? But we all know what happened to it, right? First voyage, and it sank. First voyage, right? It was built in those days using close to around $10 million, right? In today's converted rates, it's about $300 million. Still a steal, if you ask me, in terms of the kind of ship that it was, but still, it's still a lot of money, right? Now, again, right, it got wrecked in the first voyage. So, what about this one? Any guesses what happened to this? This one, again, pretty much the same kind of ship, right? Almost identical. But what they did was, after the Titanic sank, right, they actually made some modifications to it, right? You know what happened with this one? Sank as well, right? This is the HMHS Britannic, right? His Majesty's hospital ship, the Britannic, right? In terms of construction, almost the same, right? But they made some modifications, and I'll talk about that, right? Also sank. Now, if you're Harland and Wolff, the manufacturer, right, this is not good for your business, right? You build 3 of the most expensive ships ever built, 3 of the biggest ones ever built, and 2 of them sink. This was not quite the first voyage, but in World War I, it got hit by a underground torpedo, and it just sank, right? But they did make some changes, right? So what really happened with the Titanic, right? The Titanic, right, had these things called bulkheads, right? These are watertight compartments. So it was built in such a way that if 4 of the 16 bulkheads flooded, it would still be okay. Turns out, in the case of the Titanic, 5 of them, had a leak. So water started gushing in at like 7 tons per second, right? 7 tons per second. That's quite a lot of water. And what happened was the ship started getting heavier and heavier, and they had a design flaw where so the design flaw was that these watertight compartments were not actually watertight. So on top, they could actually overflow, right? And they did that because otherwise it would be very inconvenient to go from the bottom of the ship to the top. So you would have to go right back up to the top and then come back down if you had to do this. So they made a design compromise there, and he said, water cannot get to that level. It'll never get to that level. But what happens in production, right? You say it won't happen, and that's what happens. Murphy's law, I guess. Right, so the thing actually got so heavy with the water, and then it just toppled and broke in half, right? So what's the point of all this? Why are we talking about sunken ships, right? The point is that we are in changing times, right? That's Bob Dylan, if you're wondering who that is, right? He crooned that the times are changing, right? So the Titanic sank because it could not isolate failure, right? It could not isolate failure in a subsystem, and that failure just started spreading to all other systems until it took the entire system down. So our motivation was to build systems that are isolated from each other, right? So in other words, microservices is a catchy tune these days, but this has been around for a long time, right? I mean, if you look at the Unix operating system, that's the philosophy on which it was built, right? Single responsibility, autonomy, and all of this is absolutely is not new, right? The point is that now if you're small and autonomous, you get speed, and speed means lower risk, which leads to higher value. So this was our principle behind this, right? We were trying to get to faster value because at the bank, building systems faster is pretty challenging. And with large systems, it becomes even more of a challenge, right? Because too many moving parts, all of them had to align, and so it felt quite natural to actually get to an architecture which embraced smaller, independent, autonomous systems. So part 2 is really our journey. So if you look at where we started, our existing systems looked pretty much like this. I mean, this is an oversimplification, but you can get it where you've got a UI, and then you've got some middle tier, and then you've got this big large database. I guess it's fairly common to have a system like this. So what we did was in the attempt to make this to break out of this mold, we said we'll extract one piece out, a small piece, and then it's now independent of the remainder of the system. So what we could do is we could deploy it, we could build it independent of the others, and you gain some level of autonomy there, right? But if you look, it still talked to this single database, right? So what we had to do was to achieve real autonomy, we had to carve out some pieces of the data that this service would need, and then put it in its own database. All right. So that seemed to work, right? So we said, okay, fine, we're going to do this for more and more of these systems. So now what we had is we broke this down, and again, this is an oversimplification. Not all of our systems are broken down like this, but the point I try to make here is that it was done for more than just one component. So you've got this system where you've got small components talking to their own database, which means now they don't actually have to depend on each other. Well, that's not necessarily true, right? You've got these components, but these databases don't have every single piece of data that they need to do validations, to apply business logic and so on. So what we had to do was we had to now start making services call other services, right? previously what we would do was we would just go to the database. You would have another table in the database. The data would be right there, and you would just select data from there, and then now you do your validation. But now, because the data needed for this service wasn't here, it was probably here or here. So the only way you could do that is by invoking another service, right? So this caused a lot of inter-service dependencies. So it's fairly simply illustrated here, right? But you can imagine that it starts becoming a big web, right? So now we got on this autonomy journey, but we are back again where we started almost. It's now just that instead of calling databases, we are calling services. So you're like, oh, this we need to get to a better model, right? So what we did was, okay, let's see what that better model could look like, right? So what we did was we introduced this component called the event bus in between, right? The event bus is basically this thing where when something interesting happens in this component, it would let the others know by publishing an event, something that the previous presenters spoke about, right? So now that worked really well, where now when this component needed data, what it would do is it would listen to events published by this upstream component, and it would store that data in its own database, right? And now when somebody invoked this component, it already had all of the data, and it didn't need to reach out, right? So that's even more autonomous than previously. Now there's no one service calling another, right? So that's pretty powerful. So, but what we saw was when we did this, right? We saw that the UIs that invoked these services weren't able to just make one service call and get the data that they needed, right? So they needed to do that orchestration. So now, instead of doing service orchestration, you've got UIs doing that orchestration. So again, we were like, that led to this state where you've got logic that started accumulating here, right? Now you're like, oh man, this is even worse, right? We thought we wanted all of our services to become independent, and to an extent that was true. But now you've got the UIs making calls to services. They had to make them in the right order. They had to orchestrate some of them to happen in parallel, some of them in sequence. So again, not where we wanted to be. So we decided that we need yet another component to be introduced, right? We called that the API gateway, right? The API gateway now would receive a single component from the UI. It would do the service aggregation, and quite a few other things, like it would do authentication, authorization. It would do fallbacks. For example, let's say this service was experiencing a problem. It could sense that and then say, yeah, I'm going to provide some fallback response as opposed to just erroring out. So all those kinds of things happened in the API gateway, right? So far, so good. Now, but turns out, so this actually was pretty decent for us, right? This worked out well. But now we are a bank. We have to integrate with a whole bunch of third-party systems. That includes systems that are still on the legacy platform. That includes third-party vendors, partner systems, processor systems, because we are a bank, right? So you go tell some of these partners and vendors that we are event-driven. From now on, you need to publish events, right? They'll laugh you out of there, right? They're like, what? We have been here for the last 200, 300 years. We are not changing anything for you, right? So what we had to do was we said, yeah, fine, but we want to talk events and we want to be autonomous. So we introduced these things called gateways, right? So, or in DDD speak, it's an anti-corruption layer, right? So the responsibility of the gateway was to do this, right? One, it would, on the incoming side from the third party to our systems, it would translate whatever that third party would do into events, which would then get published onto the bus. So now our internal core systems, these core systems, only need to understand events. They don't need to understand the vagaries of these other systems, right? That's one. Also, what they would do is they would translate to a language or a structure that is specific to our systems. Meaning, let's say we've got two different competing third-party systems. So we are a bank. We work with processors a lot, credit card processors a lot. So now you can have processor 1 for a set of products, and you have processor 2 for a set of products. They have similar concepts, but turns out that they just call them different things, right? So we needed to protect ourselves from one system calling it an account number, another system calling it a master account number, and so on and so forth. So we had to have this ubiquitous language as domain-driven design describes it, right? So those would do, the gateways would do that translation, so that now if we have a new partner who gives us better rates, we can at least try and move to that partner without having to change our core systems too much, right? On the other side, where on the outgoing sides, they would now receive events, and they would translate it to a format that the partner understands, because now the partner says, no, I only work with batch jobs, or I only work with JMS message-based systems, or IBM MQ systems, right? So they would do that translation on the way out, right? So in general, it seemed to be an architecture that seemed to be serving us pretty well. So we went one step further with our internal core services, right? We split them up into two, and again, a lot of folks have spoken about CQRS. So where we split commands and queries into two separate things. In our case, it was logically separate. We would deploy them as one, but we are also looking at deploying them as two separate independent components, where commands are the place where you actually do things or make changes. So if at a bank, let's say I want to change my address or I want to make a payment, that's a command. Whereas when I ask for what my address is and whether I've made my payment, that's a query. So we split them out, right? So I mean, if this thing, CQRS, even now sometimes Google asks if I meant cars, so which is I guess funny, but anyway, so this thing actually was a template of an architecture which seemed to be the thing, right? We had found the answer. So finally, we have our free lunch now. Is it time for lunch, right? But you know what they say about free lunch, right? The thing about free lunch is there's no such thing, right? So there are, although this architecture seems to be serving us pretty well, right? And we went through this journey, and that's where Axon came in, right? So we did the CQRS bit, we did the event sourcing, we did the event-driven architecture, we did the domain-driven design bit, and took a bunch of help from Allard. We were on calls with him for several weeks, where we were still facing problems with this system that we had just converted to, right before going live. So I'll walk you through some of the pitfalls that you may face when you're new to adopting this style of architecture, right? So the first thing that I want to mention is this, right? I think Michael Plod, he spoke about domain-driven design and the importance of it. I can tell you that this is probably the most important thing that you'll have to do, right? You have to understand this. If you break your domain in ways that are not correct, you will end up in a lot of pain, right? And those changes will be pretty hard to reverse as well. So you better be prepared and better be well educated on these concepts, because Axon is a framework. It will do what you tell it to do, but it can't tell you how to model your domain correctly, right? That's up to you. So, but you have to get that right. Otherwise, what ends up, you've got this one big large monolith, right, which looks like a piece of candy to me. I don't know what it looks like to you, right? You might end up with lots of candy, right? And it won't be too pleasant either, right? So again, right, domain modeling, the importance of it cannot be stressed enough. You have to pay attention to it, and that only happens with techies and the domain experts sitting and collaborating very, very closely with each other. Right. The other thing that you have to keep in mind is this thing called eventual consistency, right? In a traditional system, right, you make a request and you get a response back. In that response, you know exactly whether the request that you just made was successful or not, right? But in a CQRS based system, that's not necessarily true, right? So you ask the system to do something, and if you're doing it the purest way, right, you can tell the requesting system that, yeah, I've accepted your request to make the change, right? Whether your change is actually been executed on is something that I can tell you later, right? And now the UI or the querying system has to now issue a query to find out if it was indeed successful. But that happens on the other side, right? And now if you do it really, really quick, then it's possible that the change that has happened on the command side has not yet made its way through to the query side. It usually takes a few microseconds, but it's still there is an amount of time before which they become consistent, right? And if that isn't something that works out for you, then probably CQRS isn't something that you should embrace. You can also go and negotiate with your domain experts to say that's not required, right? But you may not always succeed in that. So if you need strong consistency between writes and reads, then CQRS is something that you might want to question whether you need it or not, right? Another thing is compensating actions, right? In an ACID system, you make a request, you commit, and the database says, yes, I committed a whole bunch of these rows that you wanted me to insert or update, and after that it's good. Whereas now, because you've got these collaborating systems, an end user transaction might span multiple systems, subsystems, and multiple databases, right? So you have to be cognizant of the fact that you do something in one system and it succeeds in that system, and then now you try to do something in reaction to that in a downstream system, and that might fail, right? Fail for a variety of reasons. Maybe there's a bug, maybe there is a validation that was missed out in the upstream system. It could be or it might just be that the system in the downstream is just down. I mean, it could be a variety of things, right? So you have to be able to reverse that. And to reverse that, you have to write code, right? So it won't happen automatically where in a more traditional system you wrote code, and then if it failed, the transaction just automatically got rolled back and everything was hunky-dory, right? That doesn't work anymore. Ordering of events, I think a few of the presenters covered this, right? You have to be ready for cases where events happen out of order, right? So there are a few ways to deal with that. You can make your event handlers idempotent. You can reject events, or you can just say, I've already got, for example, in this example, I've already got event E3, so E2 is something that I'm not going to do anything about. I got it. So again, that takes quite a bit of thought, right? Or you can rely on an infrastructure to say it'll always deliver events in order, right? We try to do it in a way where we don't rely on the infrastructure, because now I can replace the infrastructure with something else, and that piece of infrastructure may scale pretty well, but may not have this event ordering guarantee, right? So you want to try and rely as little as possible on specific event orders, or as Udi Dahan, he's one of the CQRS luminaries. He says that you need to negotiate pretty hard with your business, because in the real world there are no race conditions, right? But that might not happen overnight. So you have to accept the fact that sometimes you have to deal with this. And when you have to deal with it, and when it does happen, you can't tell your customer, sorry, I mean, our system is a CQRS-based system, and events can happen out of order. You have to deal with it, which means, again, you have to write code for it and account for it, which means that somebody has to be aware, and somebody has to be able to maintain it. The other thing is, you have to be able to observe your system, right? You've got a huge number of these distributed systems. A huge is relative, right? You might have 5, you might have 10, you might have 100. And now, what used to happen in one single system is now spread across several of these systems. So you need very fine-grained control on being able to see what happened in each system, because errors can happen several days or several months even after having initiated an action, right? So that level of telemetry has to be in your systems, or you have to build it in, right? So you need monitoring, alerting, you need distributed tracing, you need log aggregation, you need health checks. All of these things have to be put in your system so that you can really reap the benefits. Because if you don't know what's going on in your systems, then I don't know what you're going to be able to tell your customers when they call and find out, hey, I made a payment yesterday, I can't see it, right? So you have to be able to tell before your customers that I've got an error in this system, so it means either I have to compensate with a compensating action, or I have to do something else, to rectify a message that is now stuck in the dead letter queue. So all of those kinds of things have to be accounted for and put in as features in your system, right? Versioning, right? Now, if you're in a world that changes, which is true for pretty much all of us, I guess, you have to be ready with making changes and making them in a backwards compatible way, right? So otherwise, you break your clients. And in this system, events more than your traditional database schema, because there is no database schema in your event store from a conventional perspective, right? Because the event becomes a blob which the database or the underlying persistence store is largely unaware of. So all of those checks that you used to get are no longer there. So now you have to write these things called upcasters, and Axon helps out quite a bit with this. But you have to have tests that make sure that you are actually maintaining backwards compatibility. Otherwise, again, when you deploy a system, only then will you know that you've actually broken it, right? Which leads me to the next thing, right? You have to have a serious amount of tests, right? And those tests have to range from unit to contract to integration to functional to performance, and they have to be in that order where you've got tests pretty much covering every single aspect of your system. Automated tests for you to be able to sustain this, because again, the same thing, right? Team 1 does this, team 2 does something else, and then now if they don't know that they're breaking each other, that's going to happen. So we have to have a test suite which firstly runs really fast and provides timely feedback before it actually makes its way into production. So automated testing is paramount for any medium to large size organization to be able to pull this off. It's definitely something that we paid a lot of attention to, and to be fair, Axon comes with a very elegant testing framework, or a testing utility, which is an extension to JUnit, where you say here is the command. Given that I've got these events that have already occurred in the past, I issue this command, and then I expect these events to be emitted or not, right? So that's definitely a big plus, right? But in addition to that, you do need quite a bit of testing in real life, because even your infrastructure pieces might have problems. So in our case, we used ActiveMQ as our event bus, right? And ActiveMQ by default makes no promises in terms of order by default. And we had to actually put it in for a little while, because our dev teams were not really at a point where they understood all of this very clearly. And a lot of it, when we started 3 years ago, even we were learning about a lot of these things, right? So CQRS and event sourcing and all of this were pretty novel even for us. So pay attention to this. Martin Fowler says this pretty nicely, right? And that you have to be at a certain level of maturity to be able to pull this off. And the question is, are you tall enough? Right? Because it's not, like I said, there's no free lunch, right? On paper, this looks like a very brilliant architecture, right? And I still believe that this is true. I lead the platform engineering capability at BarclayCard, and I firmly believe that this is the way to go, right? This is a very elegant way to scale and produce systems that are elegant and easy to maintain. But there is so much of a supporting cast that you need as well to go along with it. So you definitely have to pay attention to all of your surrounding infrastructure. The other thing, a couple of things that I haven't mentioned here is one about the continuous delivery pipeline, right? I mean, it's related to the tests that you write. You need that pipeline to be in place and automated at every single step, or most steps to be automated. Otherwise, again, you'll find nasty surprises when you deploy to production. So, what's the point? The point is that the world is changing, and so go isolate everything that you can. Thank you.
So thank you very much. There's plenty of warnings there, so we dare you. Do we have any questions at this point? Yeah.
So when you split your system, you integrate using messaging.
Yeah.
Right? So what happens when things desynchronize? How do you resynchronize them?
So let me try and understand what you're saying. You're saying things get desynchronized? I'm not sure I understood what desynchronized means.
Because you've integrated all your components using messages, right?
Yeah.
So some information which is stored in a specific microservices database is the source of truth. The rest is just replication of information stored in other systems, right? The replication, messages can get lost, bugs can arrive. What happens when the synchronization is not there? How do you resynchronize all these components?
So it's a long winding answer, but let me try, right? So firstly, I mean, we pay a lot of attention to testing, right? So unit integration and all of that. But despite that, changes do, bugs do creep in. In that case, I did speak about compensating actions, right? So what you have to do then is you have to write a compensating action to reverse that change or reverse that problem that happened, either because of a bug or because of an infrastructure issue, or because of a misrepresentation in business logic. I mean, which is again a different way of saying there was a bug, right? So the long answer or the short answer is that if those kinds of situations did arise, then it was really the last resort is a compensating action, which means let's take an example. I've got a change of address and I just did it wrong, right? So I have to have another change of address or maybe something else like that to reverse the change that happened in the first place. So yeah, there is that, and it's overhead, but with time you get better at it. Yep.
Anyone else with a question? Okay, in that case, thank you very much, Prem.
Thank you.